Proportions and triangles. Yes. More proportions, I know. Today in the proportions that we're going to be working with, we're going to be looking at how we can break apart triangles in different ways. Most often triangles. There is one that we will be looking at parallel lines, but the first one here is called the side splitter theorem. Now, it's not a big laughter thing where you're side and splitting, but hey, we're going to split our sides however you want to look at it. It says that if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. So we have triangle ABC here, and based upon this theorem, if, let's say, EF is parallel to AC, by knowing that EF is parallel to AC through the side splitter theorem, we then can conclude that this section, M, which is represented by EB, is proportional to the other parts of N, which is FB. Here is O of AE and P of CF, meaning that in order to set up the proportion, we would say M over O is equal to N over P. Those values are proportional by us just knowing that we have the parallel lines. Now, we can go back and we can think of some other theorems to where we've looked at parallel lines. What was it? The Bisector theorem. And that Bisector theorem was parallel and halfway, thinking about it halfway, if this and those were equal. So it just shows it more proportionality. All right, so let's look at it with some actual values in place. Let's get rid of these. Start plugging in some values. Say that we are told that EB is X, AE is 16, BF is 5, and FC is 10. So we want to solve for X. Now, we have the parallel lines, so simply put, X over 16 is equal to 5 over 10. So that means that they are proportional. In order to solve proportions, we cross multiply. 10x would equal 16 times 5. 10x would equal 80. Thus, x equals 8. If x is equal to 8 now, is 8 over 16 equivalent to 5 over 10? Well, they both reduce to 1/2. I've always looked at it and always like to treat it in the directions that the parallel lines go. If I extend those, that makes my proportions already. If I extend that one parallel line, x over 16, 5 over 10. Of course, we can always, if need be, plug in some expressions here. So let me erase these values. And let's use it or look at it as an expressional form. It's meaning that if here we have x plus 1.5, here is x, 5, and 2.5. We're still going to solve it in the same manner. We have parallel lines, so that one side or a parallel line is parallel to that third side. So if we extend, we have the following proportions. X plus 1.5 over x equals 5 over 2.5. Go through our cross products. Set it up. So by setting it up, we would have 2.5 times x plus 1.5. Simply these products here is equal to 5x. Solving by the distributive property, we have 2.5x plus 3.75. Plugging that into the calculator. Equals 5x. Solve them. Continue to solve. Hey, we have an x here and an x here. Move across by subtracting. So 3.75 equals 2.5x. So we would then divide the 3.75 by 2.5. Cancels. X is equal to 1.5. Now if we plug that in, let's see if that makes sense. 1.5 plus 1.5 is 3. If we plug here, 1.5. Well, half of 3 is 1.5. Half of 5 is 2.5. So that does make sense to me. Moving on. Let's look at the next theorem. Now this theorem is based upon the parallel lines. Corollary. This is the corollary to that side splitter theorem. If three parallel lines, here we go, intersect two transversals, so we have a transversal L and a transversal M. We'll just call these lines A, B, and C. Then the segments intercepted on the transversals are proportional. So it's talking about these segments right here are proportional to each other, just as we had that triangle. Because think about it, if this line was extended on up, do we not eventually have a triangle created? Yes, we do. So that's the reason why it's the corollary to that. It's not necessarily a triangle, but it is a side parallel. So, having been told that, we know that those segments are proportional to each other. So if we had x, y, z, and w, we would have the proportion of x over y equals z over w. Means that they are proportional. Plugging in, let's say that x is equal to 2, y is equal to 6, w is equal to 3. We're actually looking or solving for y in this case. Plugging in and solving, we have 2 over 6 equals 3 over w, just substituting there. Cross multiply, 2w equals 6 times 3. So 2w is equal to 18. W equals 9. So if w, we solved for w is equal to 9, does 2 over 6 equal 3 over 9? Looking at it, a quick check. Cross products work. Reducing works as well. And of course we can use expressions in that one either way. And finally, the third theorem for today is the triangle angle bisector theorem. It says if a ray bisects an angle of a triangle. So here's my ray. So we have triangle, let's say triangle ABC. And this is ray BD. So if ray BD bisects this angle, meaning those two angles are equal, they're congruent, having the same measure, then it divides the opposite sides into two segments that are proportional to the other two sides of the triangle. So here are my two segments. We're looking at segments, let's say M and N. In other words, it's AD and DC. Those two are proportional to the two sides of AB and CB. We'll call those O and P. So, how would we set this up? Now, a couple of ways to look at it. We know that proportions always, there's a couple of ways to look at it. Hey, if they're proportional, then we do have certain ways that we have to, but with the cross products, we can set them up depending on our nature, the way that we see it. Me personally, I've always seen it the way the sides are. If I can just write a little sign and put an equal sign, write my little division bar and write an equal sign, then I've got my proportion set up. Meaning I would have O over M equals P over N. The main thing here is to have the opposite numbers being multiplied. Notice M and P. I think a lot of times people have it set up differently. They are saying this side over this, O over P, is equal to M over N. Guess what? Notice we still have the same values being multiplied together. There's only a reversal of where M and P is. So either way works. Me personally, I like to just write my lines and put that equal sign across the bisector, or the ray, shows me my proportions. Well, let's get rid of some of this. There we have our proportions. So we have some values. Let's say that we're going to look for O, and P is equal to 6, and N is equal to 5, and M is equal to 8. So we're solving for O. So we'd have O over 8 equals 6 over 5. O over 8 equals 6 over 5. I know that's probably a little confusing. Put a little mark in that to show. It's not a... So 5O equals 8 times 6. So moving over here. So we have 5 times O equals 48. Now this does not come out to an equal terminate or an equal whole number. But however, if we do divide 48 by 5, it is a terminating 9.6. We don't want to round decimals, but here that terminates. So O equals 9.6. Using the triangle angle bisector theorem, making sure that if you use the ray as the equal sign, set up your proportions in that manner.